Okay, so hello class. So today we'll be discussing about nucleosynthesis. So how did the elements form from the fundamental particles of the universe. So we start with the baryonic matter in this case, which is yung ating mga protons, neutrons, and electrons. So we'll be dealing with three types of nucleosynthesis, and so let's see about kung ano yung pag-usapan natin. Okay? So, what is nucleosynthesis? Nucleosynthesis is the study of the nuclear processes responsible for the formation of the elements. And this constitutes the baryonic matter of the universe. So, from two words, nucleo, or the nucleus of your atom, and synthesis, which is formation. So we'll be dealing with the formation of the nucleus of your atoms, how they come from single particles, fundamental particles, our protons and neutrons, and then later build up into our heavy elements, the elements that we know of, and the heavier elements in our periodic table. Okay. So we'll be dealing with many different particles. Each have different um, multiple names or symbols. Some of them you might be familiar with, like your proton and neutron. What's not familiar for most people is that the proton is also termed as the hydrogen atom because one proton is a nucleus of uh, a mass number 1 and a charge of positive 1. So therefore, it's already considered an atom of the first element, which is your hydrogen. Likewise, we have our neutron, denoted by N or 0N, or our electron, by which we have letter E sometimes, or sometimes in nuclear chemistry we use beta, okay, where we write the charge of this beta particle as negative. Okay, so electron has a formal charge of -1. Here we have a combined particle which we call the alpha particle. So generally, an alpha particle is a helium atom which comprises two protons and two neutrons. And then we have massless particles like our photons or light, neutrinos, some high energy particles, and our positron, which is a counterpart of an electron, which is positive. So I think this is one of the antiparticles. Okay, so it may be denoted by E bar or positive E or positive beta particle. Okay. So where does nucleosynthesis occur? Okay, we cannot see it here on Earth, but we have to look to outer space. Okay, because everything before the Earth was in outer space. So there are three main places where nucleosynthesis occurs. Um, First is the Big Bang, second is the stars, and three in supernova. And we arrange it in this way according to which elements are being formed. Okay, so the first few elements that are very small mass happen in the Big Bang. Is where everything started. Okay, after which larger elements were made in the stars, and then elements that required a larger amount of energy were made in the supernova, which is a higher energy outer space event. Okay, so in the Big Bang, or what we call primordial nucleosynthesis, this is where the synthesis of the lightest elements occurred, and this happened in the atomic epoch. Okay, and we started a second into the Big Bang with the leptons, which was most likely discussed in the physics portion, which led to the formation of the nucleons. So all these quarks, up and down quarks, were arranged to form um, to form our nucleons, like protons and neutrons, and then after which they associated together to form our first nuclei. And primarily, the elements formed in the Big Bang are hydrogen and helium. So that's hydrogen and its isotopes having a mass number of 1 or a mass number of 2, helium and its isotopes as well, and lithium, but primarily hydrogen and helium. Okay, lithium will um, degrade after a bit. Okay. So in the Big Bang, so less than a second after the Big Bang, protons and neutrons are at equilibrium. Here's an equation showing that. So a proton combines with an electron to form a neutron that forms a neutron that is charged 0, okay, or has no charge, and then a neutrino. Okay. Likewise, the addition of a neutron with an electron forms a positive proton with an antineutrino. Okay, so this is a less than a second after. 1 to 100 seconds after, neutrons decay further. Okay, so increasing the number of protons. So there's more, the equilibrium shifts so that there are now more protons. And these protons are now the precursors to our hydrogen atoms. So protons already exist. So you can technically say there's already a nucleus present, because a proton is, in essence, a hydrogen atom. And after that, no, so once we have our proton, we now combine our proton with another neutron to form our first um, nuclide that contains two um, particles, which is our proton and neutron. And this is what we call deuterium. So it's a hydrogen isotope that contains one neutron. Okay? So more than 100 seconds after, this now leads to the formation of tritium, which is a hydrogen isotope with two neutrons here, and helium, so shown here. Here we show two isotopes of helium, one with mass number of 4 and a mass number of 3. Okay, so many reactions lead to the formation of helium, and so helium accumulates as the second most abundant element in the periodic table. Okay? So no need to get overwhelmed with the equations. These just show how nuclear reactions, things we've studied in high school and I don't think grade school, in high school, were come together to still explain how the more complex process of nucleosynthesis. Okay, so essentially we're just adding charges and mass numbers and charge numbers together to get our products here. Likewise, seconds later, we also have see the formation and decay of lithium and beryllium. And again, lithium and beryllium in the Big Bang and in primordial nucleosynthesis, they're not really emphasized as the main elements formed. Later, we'll see that stars actually form primarily from hydrogen and helium and not from lithium and beryllium. So the abundance of these elements will be very low in the early stages of the universe. Likewise, because they continue to form but decay at the same time. So they are not really favored in the primordial nucleosynthesis. And so just to summarize, each line represents a nuclear reaction. In this case, we have our proton and neutron leading up to higher and larger atoms, such as hydrogens and their isotopes, as well as lithium and beryllium. but most of the time, the Big Bang will focus on the primordial nucleosynthesis and the synthesis of this group of atoms, which is yung helium and hydrogen. Okay. So now we go on to the stars, after which, um, when all of the gaseous elements, including hydrogen and helium, condense into these atomic clouds, okay, which we call our primordial soup, due to gravitational force, those pockets of high gravity zones will now condense to form and to generate energy in the form of heat, and that will then seed the next nuclear reactions leading to our larger atoms. Okay, so when these atomic clouds then aggregate, they form our protogalaxies, which then seeded the formation of our first stars. Okay, and so from this protogalaxy, we then get protostars. And in the life cycle of a star, it's the stages that it goes through are entirely dependent on the amount of matter that it contains. So massive stars go through completely different life cycles than average stars, and stars that fail to start a new batch of nucleosynthesis, which we call our red dwarfs. So from a protostar, just a condensed mass of gas of hydrogen and helium just surrounding a gravitational center. Depending on the amount of matter, we can get a red dwarf if it's very deficient. So it would fail to start the combustion of hydrogen. Um, Otherwise, we get a average star if we have much more matter. And this is where our sun is currently at. We have a sun as our average star, and in the end of the sun's lifespan, it will turn into a red giant, meaning that it's nearing the end of its lifespan. And then that shell, once depleted, will expand to form our planetary nebula. And then what's left in the center is our white dwarf. But for stars which are larger than our sun, probably around 8 solar masses larger, we get a massive star. Okay, and massive stars sometimes burn brighter and have processes that lead to even heavier elements being formed. But in the end, they will proceed through the same phase as our sun and form a red supergiant. And that red supergiant, once it reaches a critical nucleosynthesis point, wherein they form iron, okay, will explode to form what we call our supernova. So it's a more cataclysmic and bright explosion compared to just the expansion of the shell from a planetary nebula. Likewise, it's very the products or the remnants of the star are much more dramatic, so to speak. Um, the dramaticness can be seen in two ways. So one is the black hole, something that's been recently imaged. It actually looks quite like this in the actual image. Of just recently, they were able to generate an image of a black hole. Likewise, another thing that is a remnant of a supernova is our neutron star, which is a highly dense star, by which some say that a teaspoon of a neutron star matter is equivalent to the mass of a large truck. That's how dense a neutron star is. Okay, so that's the life cycle of a star. So in between these points, in massive stars and average stars, what are the elements being formed? So that's what we'll explore today. Okay. So in intermediate mass stars and early massive stars, such as our sun, they proceed through a hydrogen burning phase to form helium. Okay, and this burning is represented through an equation or a um, nucleosynthesis chain we call the proton-proton chain reaction. Okay, so it's essentially described as the merger of two protons to form our deuterium here, mass number 2 of hydrogen. When combined again with another, forms tritium. And then when two tritium atoms converge, they form a hydrogen atom and another hydrogen atom and then helium. Okay, so it forms three types of or two types of nucleons. So uh, I'm sorry, this is not tritium pala. This is helium within an helium-3 isotope. So when two helium-3 isotopes converge, they form our helium, or what we also call our alpha particle. Okay, and this is the primary method by which stars undergo nucleosynthesis. Stars that are the mass of our sun. Okay, and here is the equation that summarizes the transformation: two protons to tritium, tritium to helium-3, and then two helium-3 to helium-4, or with two protons as its product. So you can balance this out, and it actually balances out to just uh, adding hydrogen atoms to form our helium. Okay, so it's cyclic in nature. It goes back and returns and then continues to form. Okay, so from protons we get helium. In massive stars and red giants, we observe a different kind of hydrogen burning, which we call the Cno cycle, or the alpha process. So what this does is that it uses a cycle containing three kinds of intermediate mass atoms, such as carbon, nitrogen, and oxygen, to process protons together and then form helium at the end. Okay, so um, it the protons or hydrogen atoms feed into this cycle to form our helium. Okay, so usually it's not really shown as a layer of burning, um, because realistically, stars um, do their burning sequentially. So there wouldn't be hydrogen burning anymore if it reaches the stage where it's already burning iron, for example, because um, it's not just a function of the location of the stars, of the layers of the star, but also a function of time. Okay, so in essence, the CNO cycle condenses into this equation, wherein four protons are converted into a helium atom, which the charge of the protons are processed as neutrinos and gamma particles. Likewise, there's another process for even larger stars, which they call the triple alpha process. Okay, so in the triple alpha process, three alpha atoms, or our helium atoms, form a carbon atom, and then another reaction forms our oxygen. So you may be wondering where the carbon and oxygen came from the CNO cycle. This is where they come from. So in the triple alpha process, it forms carbon, and then addition of another helium atom forms our oxygen atom. Okay, and you may be wondering why electrons are not part of this? Well, generally in a hot environment, electrons are less likely to associate with the atoms. So, in most nuclear reactions, electrons are usually forgoed. Okay, so nucleosynthesis really focuses on the nucleus itself. So here's a summary of the triple alpha process. So there's the transient formation of beryllium, and then by three alpha particles, we form our carbon. And from carbon, we form oxygen in what we call the C alpha gamma oxygen reaction. Okay? And in the end of the lifespan of a red giant of intermediate star, the outer shell of the star expands to form our planetary nebula. And it's not called a planetary nebula because it's used to form planets, but it's named that way due to their symmetric or planet-like shape, as opposed to supernova, which are kalat, pakalat-kalat yung kanyang explosion. Pero yung planetary nebula, symmetric yung kanyang shape, because medyo procedural yung kanyang pag-explode. Okay? So, shed off lang siya ng shells. Kaya as you can see here, yung Helix Nebula, which is a planetary nebula, you can see na very symmetric siya. Mukha siyang mata. Ayun. Tapos, meron siyang gitnang star, which we call our white dwarf. And planetary nebula are the likely endpoint of the sun after its life cycle of about 1.6 billion years. So medyo matagal pa yan, no? Hindi na kayo buhay nun. Pero some people may expect na yun yung end ng ating solar system. Okay? So that's about 1.6 billion years pa naman. Okay? So that's the planetary nebula. So from that, okay, that's planetary nebula. That's for intermediate stars. But now, how do we deal with yung mga stars na larger than our sun or giant stars? Okay, so from the carbon formed in regular stars, we now proceed to larger and larger atoms. Okay, so we proceed through carbon burning, by which carbon is converted to magnesium, and larger we also get some byproducts like neon. We also have a neon burning process by which oxygen can form neon, and neon can form magnesium as well. And the oxygen burning process as well continues, oxygen burning to larger atoms like silicon. I think that really jumps the periodic table, down the periodic table. And then silicon burning to magnesium, and then silicon burning in multiple steps to get our final iron. Okay? So in iron, that marks the end of a massive star's lifespan, because once it starts forming iron, it cannot sustain the energy anymore and has to undergo a supernova. Okay? But before that, what happens is there are simple processes that occur in the star while that is happening. Okay, so the processes that can form elements larger than iron are what we call our S processes and R processes. In non-supernova stars, or stars that have not yet undergone supernova, they may form the elements heavier than iron through what we call our neutron capture reaction. Okay, so in neutron capture, an atom or a nucleus obtains neutrons, so the mass number increases, but due to the large number of neutrons, the neutron decays by beta decay into a proton. Okay, So in effect, the charge increases and the mass increases. Okay, so it moves in a diagonal way. Okay, it increases its mass, it increases its charge. Okay, so what we call the S process for this is S for slow, and the S process occurs in asymptotic giant branch stars. So giant meaning they are larger than our sun, and they are a specific color and size cluster. This process proceeds alongside the helium burning, so not supernova hasn't been happening yet, and it produces elements heavier than iron up to bismuth. Okay, so it cannot really form elements larger than bismuth. Okay, so here's how the S process looks like. This is just an example or a segment of it, which plots from silver up to tellurium. Okay, let's get a better look. So here in the S process, every line that goes to the left, to the right, is an increase in the number of neutrons. So this is the neutron capture. And then when it goes upward, okay, there is a increase in the number of protons, but a decrease in the number of neutrons. So this is our beta decay, these diagonal lines. So we have a neutron capture and then a beta decay, multiple rounds of neutron capture, beta decay, neutron capture, beta decay, and so on and so forth. Okay, so that's the basic process by which the S process proceeds. Okay, and you can zoom out of this and see that there are many other processes by which the the stars form these larger elements. And you can zoom out even further to see the end point of SDS process and another process which we call the R process path. Okay, so we'll discuss the R process path because the R process path doesn't happen in normal stars. Okay, it doesn't happen in normal stars. It happens in our supernova. So in the supernova or supernovae, we encounter a stellar explosion at the end of the red supergiant phase of supermassive stars. The star explodes and collapses into either a neutron star or a black hole. And this process includes nucleosynthesis through the R process. Okay, because this is a very high energy event, it releases a high amount of light. Okay, so how scientists were able to see supernova in action was that they observed the sky to see if large, like bright, uh, bright light spots appeared, which signified that one of the stars went into supernova within a span of just a few days. Okay, so here we have one of the iconic supernova images or supernova remnant images, which is yung Crab Nebula. So in between that, I'm not sure if it's a neutron star or a black hole, but you can see that it's not symmetric. No, there are many lobes you can see, and each of those lobes may contain high or each of these clouds may contain ha- elements that are heavier than iron. Okay, and um, and they determine the composition of the of the clouds using light or the wavelengths of light that they observed. So in a supernova, it's a big explosion, asymmetric, so it's not clean at all, but it forms one of the heavier elements in our universe, right up until possibly uranium. Okay, so again, the formation of those larger elements are due to the R process. R signifying rapid, and it occurs in supernova and neutron star mergers. Okay, so not only in supernova, beginning with modern astronomy, they also found that um, new, most of the systems in the universe or star systems in the universe don't just have one star. Okay, so sometimes, or most of the time actually, they found that two stars can be in the same system. And then when those two stars merge, okay, there it's also a large energy event which causes our process nucleosynthesis as well. So those processes produce neutron-rich isotopes of elements which are heavier than zinc up to plutonium, so very heavy elements, and require a neutron-rich environment for neutron capture. Okay, so again, um, neutron-rich environment for neutron capture, again, because our process proceeds much like S process, in which it requires neutron capture and then beta decay. So it's just a little less clean. As you can see, it's denoted by a shaded region because it's a very spread out process. Okay. So in essence, this is the periodic table of the origin of the elements. You can see the Big Bang produced majority of our hydrogen and helium, or almost all of our hydrogen. And then um, through fusion in stars, we get our elements here, like up to iron, starting with helium up to iron. And then from cobalt onwards, we get the slow process neutron capture. Okay, and then likewise, we also get rapid process neutron capture from the R process, here labeled in green. And then here we also have synthetic elements. So astonishingly, some of the elements we were able to create um, were because of our experiments in nuclear synthesis. So some of the elements here can be attributed to endeavors of mankind, so to say. So so it's amazing to see that we have these new elements that are shown to exist, albeit very short-lived, no? So nagde-decay din sila very rapidly, and then that's why they're not really found in in nature. Okay, well, nature in the world, the universe. Okay, so that's on the origin of the elements.